Seismic analysis of structures by Etabs in BS code and IS code. Abstract earthquake has become popular in 20th century in whole world. It's relating with safety, so we must be care about designing an analysis of earthquake. Since past earthquake happen in expected countries in expected part in continent. Nature disasters had changed from time to time, even climate affected by time, so in modern century and development of knowledge there is no expectation where our disasters will happen, just we must be ready to provide and protect humans. When we are talking about earthquake, we must know that we are talking about human souls in two options, death or live. There is no other choice. As we are engineers, we learned in college about foundations of engineering, especially in civil engineering. When we are going to design structures, we must keep constant principles are safety, architecture view, and finally economy. So I always remember myself by occupation moral and follow it. Due to importance of seismic analysis in whole structures, I am going to talk about it in my project. I will do seismic analysis and design by Etabs with IS code because I am doing it in India, and with BS code because I am from Africa. We follow BS code. So main aim of my project is comparative between IS code and BS code in seismic analysis of structures by Etabs. Keywords: seismic analysis, structures, data, analysis, design, comparative. 1. Introduction. The vibrations arising from earthquakes are characterized by randomness, as the soil vibrates in the earthquake zone in various directions, which causes a variable ground acceleration that affects the foundations of origin located in the earthquake area, which in turn affects the elements of the structural structure that vibrate and generate internal forces related to the amount of acceleration due to the earthquake as well as the mass of these elements. In general, the ground acceleration due to earthquakes can be expressed by horizontal and vertical vehicles, except that the vertical vehicles are neglected due to the fact that the vertical hardness is very large and the focus is on studying the installations to resist the horizontal vehicles to acceleration only. Seismic analysis of facilities can be divided into two main groups. 1. Methods of static analysis. 2. The methods of dynamic analysis include: A. Nonlinear analysis methods. B. Methods of direct integration of the motion equation. C. Methods of phasing analysis using response spectrum charts. Dynamic analysis is used in the following cases. 1. The height of the origin exceeding 75 m. 2. A difference in the floor height of any floor in the building. 3. A difference in the structural sentences and in the building materials formed for each of them. 4. A big difference in the shape of the horizontal projection between the repeated floors. 5. The non-continuation of one of the structural elements, column or shear wall, throughout the entire building height. 6. A big difference in the distribution of the interior partitions between successive floors. The results obtained in various ways may be characterized by significant differences due to the nature of the assumptions used in each of them. Therefore, choosing the appropriate method for the studied structure depends on several factors and the experience of structural engineer. The following table can be used to choose the appropriate method. Type of origin: seismic analysis method. Small facilities. Static analysis method. Huge and complex installations. Nonlinear analysis method. Medium-size facilities. Direct integration method. Larger and more complex installations. Phase analysis method. Explanation of the static analysis method. This method relies on converting the seismic dynamic forces into equivalent horizontal static forces that affect the building in a horizontal direction, according to the main axis of the building. This method is used in the case of small installations or almost regular shapes with a section that is fixed or semi-fixed at its entire height, and that the decline in the horizontal projection does not exceed 25% of its area on the upper floors. Calculate the equivalent horizontal forces. The static analysis method depends on finding the horizontal force caused by the earthquake and applied in the base of origin level, called the base shear force. Coefficient C. It is called the seismic coefficient of the region in which the studied origin is established, bearing in mind that the seismic map approved in the Arab world includes 5 seismic regions. Modified Mercury scale description of the region factor Z region number. Smaller than 1 is not prone to 0 earthquakes. 0. 1 is not subject to 0.1 strong earthquakes. 2 area of moderate seismic damage 0.2. 3 region with major seismic damage 0.3. 4 greater than 3, a region with damaging seismic damage 0.4. Parameter K. This coefficient represents the inelastic, plastic, behavior of facilities when exposed to seismic loads, and its value decreases as the building compliance increases, and its value is taken from the following table: characteristics of the structural sentence, laboratory K, high water tanks and the like, carried on a group of columns not less than 4, and adequately connected horizontally in both directions. 2.5 Special establishments, chimneys, minarets, television towers, cooling towers. 2 installations carried out from load-bearing walls of reinforced concrete, planed or in a vacuum shape, shear walls or central core. 1.3 Installed buildings or buildings of structural or mixed construction frameworks according to the following design case: A. Tires and shear walls together resist horizontal loads. B. The shear walls are calculated to bear the entire horizontal load. In both cases, the flat or vacuum tire resistance must not be less than 25% of the total horizontal loads. 0.8. 1.1 Objectives. This study focuses on comparison of international standards. The chosen standards are British Code, British Society of Civil Engineers, and Indian Code, i.e. is 1893:2002. The study also helps in understanding the main contributing factors which lead to poor performance of structure during the earthquake, so as to achieve their adequate safe behavior under future earthquakes. The structure analyzed is symmetrical, G+10, modeling of the structure is done as per Etabs software. 1.2 Methodology. The methodology worked out to achieve the mentioned objectives is as follows. Point 1. Modeling of the selected building in Etabs software. Point 2. Retrieved time history and response spectrum of structure from the software. Point 3. 2 models as per the codes, i.e. Indian Code, British Code specification were made. Point 4. Calculated push analysis seismic forces and load combinations as per IS 1893-2002, and BS 8110-1997. Point 5. Analyzed the models of the data is presented to evaluate stability. 2. Literature review. A. Kale, S. A. Russell, 2017. In this proposed study, 4 different shapes of same area multi-story model is generated and tested by the Etabs under the guideline of IS 875 Part 3 and IS 1893-2002 Part 1. The behavior of 15, 30 and 4H 5-story building has been studied. The dynamic effects also find by response spectrum method. All the parameters like story displacement, story drift, base shear, overturning moments, acceleration and time period are calculated. After comparing all building shapes, results concluded that which section is convenient and either seismic or wind effect is critical. Gauri G. Kakpur, Ashok R. Muhaned, 2016. This paper presents a review of the previous work done on multistoried buildings vis-a-vis earthquake analysis. It focuses on static and dynamic analysis of buildings. This paper presents a review of the comparison of static and dynamic analysis multistoried building. Design parameters such as displacement, bending moment, base shear, story drift, torsion, axial force were the focus of the study. G. Guru Prasad, 2017. Performed a dynamic analysis of G+15-storied RC frame building with L, C and rectangular Shapian plan with the help of Etabs software. Comparison has been done by considering the parameters such as story drift, story shear, support reactions, building mode, and section cut force. It has been concluded that maximum value of story shear was observed for L-shaped plan than rectangular building and C-shaped building. The story's drift values in X direction and Y direction increases for top to bottom story in all 3 cases. When earthquake load is applied in Y direction, it was found that irregular plan structure can resist more base shear than rectangular plan structure. Regular building and L-shaped buildings gave good results than C-shaped buildings in all aspect. Athill-Yaolas, 2017. Performed wind analysis of buildings having various shapes such as Y plus and V. Buildings of plan shapes Y plus and V are modeled in Etabs 2016 and analyzed. It is observed that the story force is same for all the buildings, i.e. the story force does not change with the shape. The lateral displacement is found maximum for V-shape building. The story drift is observed maximum for I shape as compared to that of other shapes, and the lateral displacement and the story drift are observed minimum for plus shape building as compared to Y and V shape buildings, and hence it is the most structurally stable shape among the selected shapes. Pradeep Pujar, 2017. Analyzed G plus 9-storied irregular buildings to find their seismic performance with and without shear walls. Shapes off building plan considered for the study were I, L and C3 models of bare frame and 3 models with shear walls were considered for the study. The models has been analyzed by equivalent static technique with the assistance of Etabs v15.0.0 programming. The comparison has been done by considering the parameters such as story displacement, story drift and base shear. It has been concluded that L-shape, C-shape structures with shear walls are having great outcomes in base shear, story drift and displacement. In all shapes, the I-shape building with shear wall is having increased base shear both in X and Y direction, and the L-shape is having very less increased base shear. The building with shear wall gives better execution against the seismic tremor when compared with bare frame building. Aniket Akale, 2017. Carried out the wind and seismic analysis 15, 30 and 45-storied buildings of 4 different shapes of same area by using advanced software CSI Etabs. Response spectrum method was used to find the dynamic effects. The comparison has been done by considering the parameters such as story displacement, story drift, base shear, overturning moments mz, acceleration and time period. It has been concluded that for maximum earthquake structure of 15-story is most stable structure, and for maximum wind effect triangular structure of 15-story is most stable. For 45-story circular and rectangular shape building is most stable for maximum earthquake and wind effect respectively. Wind effect is critical for 45-story building, and on the other hand seismic is critical at 15-story and 30-story building. Wind effect is more critical than earthquake. Pardeshi Samir, 2016. In this study, 3D analytical model of G plus 15-storied buildings have been generated for symmetric and asymmetric building models and analyzed using structural analysis tool Etabs software. Mass and stiffness are 2 basic parameters to evaluate the dynamic response of a structural system. This paper is concerned with the effects of various vertical irregularities on the seismic response of a structure. The objective of the project is to carry out response spectrum analysis, RSA, of regular and irregular RC building frames and time history analysis, THA, of regular RC building frames, and carry out the ductility-based design using IS 13920 corresponding to response spectrum analysis. Comparison of the results of analysis of irregular structures with regular structure is done. S. Mahesh, B. Panduranga Rao, 2014. In this paper, a residential of G plus 11 multi-story building is studied for earthquake and wind load using Etabs and STOS Pro VAI. Assuming that material property I linear static and dynamic analysis are performed. These analyses are carried out by considering different seismic zones, and for each zone the behavior is assessed by taking 3 different types of soils, namely hard, medium and soft. Different response like story drift, displacement, base shear are plotted for different zones and different types of soils. SKA Hirewar, SK Jain, and Pandey, 2008. This paper presents the seismic load estimation for multi-story buildings as per IS 1893 to 1984 and IS 1893 to 2002 recommendations. For multi-story RC framed buildings ranging from 3-storied to 9-storied are considered and analyzed. The process gives a set of 5 individual analysis sequences for each building, and their results are used to compare the seismic response viz. Story shear and base shear computed as per the two versions of Seismic code. The seismic forces, computed by IS. 1893 to 2002 are found to be significantly higher. The difference varies with structure properties. It is concluded that such study needs to be carried out for individual structure to predict seismic vulnerability of RC-framed buildings that were designed using earlier code and due to revisions and thecatal provisions may have rendered unsafe. Dr. Sanjay K. Kulkarni 2018. This paper presents the seismic load estimation for multistory buildings as per IS. 1893 to 2002 and IS. 1893 to 2016 recommendations. The method of analysis and design of multi-story, G+4, residential building located in Zone 3, 4. The scope behind presenting this project is to learn relevant Indian standard codes are used for design of various building elements such as beam, column, slab, foundation and staircase using a software Etabs under the seismic load and wind load acting the structure. To find out the values in project base shear, time period, maximum story displacement. Gauri G. Kakpur, 2017. Reinforced concrete, RC, building frames are most common types of constructions in urban India. These are subjected to several types of forces during their lifetime, such as static forces due to dead and live loads and dynamic forces due to earthquake. In the present work, two tall buildings, AG+10 and AG+25 structure, presumed to be situated in seismic zone 3, are analyzed by using two different methods viz. Equivalent static analysis method and response spectrum method, using Etabs software. From analysis results, the parameters like story drift, story displacement, axial load, bending moments are determined for comparative study. Results established the superiority of the response spectrum method over the equivalent static analysis method. Story drift value for G+10 and G+25 are 22 to 25% less respectively, in dynamic analysis than static analysis. All the values are within the limits as per code requirement. As the height of story increases, the displacement values too gradually increase. Top story has maximum displacement value in both XY directions. For dynamic analysis, story displacement for G+10 and G+25 buildings are 22% and 26% less than the corresponding values in static analysis. B. Jairesh Babu, 2017. In this study the seismic response of the structures is investigated under earthquake excitation expressed in the form of member forces, joint displacement, support reaction, and story drift. The response is investigated for G+7 building structures by using STD-Pro designing software. It's observed the response reduction of cases ordinary moment resisting frame. In this case, we have taken earthquake zone 2, response factor 3 for ordinary moment resisting frame and importance factor 1. Initially started with the designing of simple two-dimensional frames and manually checked the accuracy of the software with our results. Then according to the specified criteria assigned it analyzes the structure and designs the members with reinforcement details for G+7 residential building RCC frames. In the earthquake-resistant design of G+7 arc-framed building the steel quantity increased by 1.517% to convention concrete design. The steel quantity increased in the structure ground floor to higher floor i.e. G+7 level of the structure. The story drift condition for considered G+7 building, the base drift equals 0.0 at every story. This says that the structure is safe under drift condition. Hence shear walls, braced columns are not necessary to be provided. Hence story drift condition is checked for the G+7 building. 3.2 Analysis by IS code. 1. Structure data. This chapter provides model geometry information, including items such as story levels, point coordinates, and element connectivity. 1.1 Story data. 5. Discussion. In this chapter we will discuss analysis and design results, especially affected factors and values obtained like response spectrum, diaphragm acceleration, story stiffness, design beams, design columns, design piers. 5.1 Response spectrum functions. Response spectrum is a plot of the peak or steady-state response, displacement, velocity, or acceleration, of a series of oscillators of varying natural frequency, that are forced into motion by the same base vibration or shock. The resulting plot can then be used to pick off the response of any linear system, given its natural frequency of oscillation. One such use is in assessing the peak response of buildings to earthquakes. The science of strong ground motion may use some values from the ground response spectrum, calculated from recordings of surface ground motion from seismographs, for correlation with seismic damage. BS. Asterisk from above result we saw acceleration values of response spectrum in BS code is higher than IS code. BS code approved. 5.2 Diaphragm accelerations. Accelerations are needed to evaluate in-plane diaphragm forces in earthquake-resistant design of buildings, and for the design of their connections. Recorded floor accelerations in buildings during some past earthquakes have shown acceleration magnifications that are not properly considered by current building codes. Earthquake damage in some precast buildings seems to point out significant deficiencies in the design of precast diaphragms. BS. Asterisk from above table we observed that shear X and shear Y in BS code is higher than shear X and shear Y in IS code for story 10. Asterisk we observed also drift X and Y in BS code is higher than drift X and Y in IS code for story 10. Asterisk we observed also stiffness X and Y in BS code is lower than stiffness X and Y in IS code for story 10. IS code approved. 5.4 Deasing of beams. A beam is structural elements that primarily resists loads applied laterally to the beam's axis. Its mode of deflection is primarily by bending the loads applied to the beam result in reaction forces at the beam's support points. The total effect of all the forces acting on the beam is to produce shear force and bending moment within the beam, that in turn induce internal stresses, strains, and deflections of the beam. Beams are characterized by their manner of support, profile, shape of cross-section, equilibrium conditions, length, and their material. Asterisk from above tables of beam design we observed that required area rebar of IS code is higher than BS code then moment values and required steel bars in IS code is higher than BS code. BS code is approved. 5.5 Design of columns. A column is a vertical structural member intended to transfer a compressive load. For example, a column might transfer loads from a ceiling, floor, or roof slab or from a beam to a floor or foundations. Columns are typically constructed from materials such as stone brick, block, concrete, timber, steel and so on, which have good compressive strength. Asterisk from above tables of column design we observed that required area rebar of IS code is higher than BS code then moment values and required steel bars in IS code is higher than BS code. BS code is approved. 5.6 Design of piers. In general, it is an upright support for a structure or superstructure, but it can also refer to the sections of load-bearing structural walls between openings and different types of column. Piers are most commonly made of concrete, masonry or treated timber, and installed into prepared holes or shafts. And can also be used in foundations as a means of raising a structure from the ground, in particular if the structure is on a slope or near a large body of water. Asterisk from above tables of piers design we observed that required area rebar of IS code is higher than BS code then moment values and required steel bars in IS code is higher than BS code. BS code is approved. 6 Conclusion. From above tables analysis it is observed that base reaction and center of mass and rigidity values in IS code are higher than values in BS code, T 3.1 and 3.2. From above tables analysis it is observed that center of mass displacement and diaphragm acceleration values in BS code are higher than values in IS code, T 3.3 and 3.5. From above tables analysis it is observed that response spectrum modal information and story max/average displacement and story drift values in BS code are higher than values in IS code, T 3.6 and 3.7 and 3.8. From above tables analysis it is observed that story forces values in BS code are higher than values in IS code, T 3.9. From above tables analysis, it is observed that story stiffness values in IS code are higher than values in BS code, T3.10. From above tables analysis, it is observed that modal period and dynamic load participation ratio and modal direction factor values in BS code are higher than values in IS code, and frequency and eigenvalues in IS code are higher than values in BS code, T3.11 and 3.13 and 3.14. From above tables design, it is observed that shear force values in IS code are higher than values in BS code until story 7, and for story 8, 9 and 10 values in BS code are higher than values in IS code. From above tables design, it is observed that for all stories rebar percentage values in BS code are lower than values in IS code. From above tables design, it is observed that shear force and reinforcement values in IS code are lower than values in B.S code. Images shows. Displacement of structure after analysis. Moment diagram of wind X. Moment diagram of RSX. Moment diagram of combo 1.5. Shear force diagram of combo 1.5. Response spectrum chart.